Howdy. So we have a problem here that states we have two lines of charge with two separate line densities. So we have the first linear charge density, which is equal to 4.58 times, or 4.58 microcoulombs per meter. And then we have a second line of charge, which is negative 2.56 microcoulombs per meter. And it states that this first one uh, this is at y equals 0 meters on the x-axis, and this one lies on y equals 0.4 meters, parallel to the x-axis. So let me see if I can draw that out real quick. So we have got, let's see. Okay, so we have, um, we'll call that the first linear charge density, and then we have a second one about 0.4 meters above that. So that'll be second linear charge density, and we want to find out the uh, electric field at the point 0.2 meters on the y-axis. So we will be using Gauss's law to determine this. And if you don't remember Gauss's law, essentially it states that um, I'll just write it out the form of it. So the integral of the electric field vector and with the dot product of the area vector will give you the flux through an area, and that also equals the charge enclosed in within the area divided by epsilon naught, the constant. So furthermore, this can be simplified down because you can choose any shape for Gauss's law. So this can be simplified further. If you think about it, the one of the forms of dot products is just the magnitudes of the separate vector components times the cosine of the angle between them. And oftentimes, when you pick the shape, it can be a sphere, it can be a cylinder for the surface area of either of these. The electric field line will be exactly parallel to the surface area. So if we choose a cylinder, we'll choose a cylinder in this case for this problem. We'll have a cylinder going around this line right here with a radius of uh, 0.2 meters, and we'll make it an arbitrary length. You'll find out why we can do this in just a moment. So we'll have that cylinder around it, and we will have the electric line, field lines coming off of this line of charge coming out that way. And similarly for this one, I won't draw the whole thing out, but we'll have the lines drawn to it because it's negative on this line of charge, so it will be attracting the electric field lines. This will be pretty important to take note of later when we're actually solving the final problem. But let me simplify this down further. So the area vector coming off of the surface of the cylinder will be will end up being perpendicular at all points, or sorry, parallel to all points to the electric field vector. So basically, you can say that the angle between them will be equal to pi r0. Actually, it will just be equal to 0. And since the cosine of 0 is just equal to 1, you can just rewrite this as the integral of e dA, which then further simplifies to e times a, and that will still equal out to the charge enclosed divided by the epsilon naught. Okay, so you may be wondering how we're going to use the linear charge density when we can't figure out when they haven't given us a set length to find out the charge enclosed. And here's the cool part. First, let me write out the area for the part of the cylinder that we're looking at. We'll be looking at the surface area of the long side of the cylinder, which is just the circumference of the circle, 2 pi r times the length of this cylinder. We'll call it L. So the area of that cylinder will be that, and we can plug it into our equation here. And we've got 2 pi r L times the electric field equals the enclosed charge divided by epsilon naught. And when you think about it, the linear charge density is just equal to the charge, or just the charge divided by the length. And that's the cool part here. You might be already starting to see how this takes place, or takes form, but we'll just solve it for the electric field, and we have charge enclosed divided by epsilon naught, 2 pi r times the length, and this essentially becomes the charge density. So we'll have the charge density divided by 2 pi r epsilon naught. Okay, so we have our equation that we will be plugging these into. So let's start with the bottom one. For the bottom charge density, we'll have charge density 1 divided by 2 pi, and I'll write in 0.2 meters for the radius, or the distance on there, and times epsilon naught. And then we'll have plus. Now here's where that sign convention comes in handy. You have to remember that the electric field from both these lines is pointing in a positive direction. So you can essentially ignore that this is negative. Of course, it's important that it's negative. It tells you that it's going in a positive direction. But you can just say that both of these are being added together. And in this case, the bottom will be 2 pi. And in this case, the distance is the exact same. So it'll still be 0.2 meters for this. which comes in pretty handy because then we can just combine these. We don't have to solve them separately. So we'll have this, the two linear charge densities add together divided by the 2 pi times 0.2 epsilon naught. And once again, don't pay too much attention to the signs on this because that was handy in telling us which way the electric field lines were going. But essentially, we can just add these together at this point since we know which way the field lines are going. So this will just come out to 4.8 or 4.58 plus, we'll say that because we can just, like I said, we can just add them together divided by 2 by 0.2 epsilon naught. And let me just get my calculator out real quick. As you can see, I've tried solving this before, but we'll give it another shot real quick. So we've got 4.58 plus 2.56 divided by 2 divided by pi divided by 0.2 divided by 8.85 for the epsilon and divided by 10 to the negative 12. And remember that this is in microcoulombs per meter. So that means that it's 10 to the negative 6. So we'll have to factor that into our calculations. So this will be times 10 to the negative 6. And that will give us our answer here, which will be 6.4 times 10 to the 5th power.